In this video, we're going to look at how to calculate the pH of a buffer solution after a strong acid or a strong base is added to it. If you haven't already watched the videos that talk about what pH buffers are in general and how to calculate the pH of a buffer that hasn't had anything added to it, then I would advise watching those videos before you watch this one. Firstly, let's look at questions where we add a strong base like sodium hydroxide or potassium hydroxide to an acidic buffer. The trick to answering these questions is to recognise that really they're an equilibrium question. So you need to use Le Chatelier's principle and probably lay out the start of your calculation in the same way that you would do for an equilibrium question from the Kc topic or the Kp topic. If we add some sodium hydroxide or another alkali, then those alkalis contain hydroxide ions. And the hydroxide ions that we're adding will react with the hydrogen ions that are present in that solution having come from the weak acid. So when those hydrogen ions and hydroxide ions react together, they're going to form some water. Le Chatelier's principle tells us that when this happens, the system will shift to counteract the change. In other words, having removed those hydrogen ions, the system is going to shift to produce more hydrogen ions. And the only way it can produce more hydrogen ions is by the weak acid further dissociating. Now, in terms of numbers, for every one hydroxide ion that you add, that's going to be responsible for the removal of one hydrogen ion. And that one hydrogen ion is going to come from one acid molecule. So for every mole of hydroxide ions that you add, we're going to dissociate 1 mole of weak acid in order to replace the hydrogen ion. Now the weak acid is made up of the hydrogen ion but also an anion. So as the weak acid dissociates, we replace the hydrogen ions that have been removed by the hydroxide ions, but we also produce new anions at the same time. Once you've worked out the moles that remain of the weak acid and the moles of the anion that have been produced, we can convert those back into concentrations by dividing by the total volume. And remember that that total volume could have up to 3 parts: the volume of the weak acid, the volume of the salt solution that was added to the weak acid to make the buffer, and then also the volume of the strong base that you are adding. Once we have these concentrations, we can then use the acid dissociation constant Ka in order to determine the new concentration of hydrogen ions. And once we have that, then we can determine the pH. Here's one example of an exam question that you might encounter. Now, typically this wouldn't be part 1 of the exam question. You would usually start with a shorter question where they ask you to calculate the pH of the buffer when it's first made, and then this question would be part 2, in which you're asked what happens to the pH when some strong acid or some strong base is added. But here we're just going to jump straight in, and if you do need some more practice working out the pH of pure unadulterated buffers, then you can look at the previous videos to see how you can do that. We're going to treat this question very much as an equilibrium question. So think about Le Chatelier's principle and the questions that you answered using that when you were in year 12. And we want to lay this out in a very similar format. Now, obviously the exam board are not going to give you a grid like this in the exam, but it's quite easy to learn how to do this, and using it will help you to lay out your calculations in a really systematic way so that the marker can see what your thought process was. And even if you don't get the right final answer, it helps you to get some of those intermediate working marks because it's very clear what you were doing. So firstly, I'm going to write down what the initial concentrations of the solutions that we used to make my buffer were. So I've got 0.8 molar ethanoic acid and 0.4 molar sodium ethanoate. And of course, the reason that I've picked that salt is that it contains the same anion as the acid that is being used to make the buffer. Then I can use concentration multiplied by volume to work out how many moles of each of those substances I had when the buffer was first made. So concentration multiplied by volume gives me 0.012 moles of ethanoic acid and 0.010 moles of sodium ethanoate. Now, of course, those moles are going to change when we add this strong base, which is the sodium hydroxide. So every 1 mole of sodium hydroxide will react with 1 mole of the hydrogen ions that are in the solution from the acid, because a little bit of it is dissociating even though it's a weak acid. So the hydroxide ion and the hydrogen ion join together to make water, which is effectively removing those hydrogen ions. And then, of course, what will happen is that the weak acid will dissociate to produce the same number of hydrogen ions that we've just lost. So for every 1 mole of sodium hydroxide that we add, we're then going to dissociate 1 mole of ethanoic acid. So that's going to replace the hydrogen ion, and the concentration of the ethanoic acid will decrease. And then at the same time, we'll have those leftover anions that they were associated with the hydrogen ion to make the weak acid, but they no longer are. So we're going to have the concentration of the anion increasing. Again, I'm going to use concentration times by volume. So I've only got 1 centimetre cubed of sodium hydroxide. So 0.5 times 0.001, because of course this needs to be in decimeters cubed, and that gives me 0.0005 moles of sodium hydroxide. So that's the number of moles that we're going to see decreasing for the ethanoic acid, and the number that is going to be increasing for the anions. So now I can put those together with the previous line of my table to work out how many moles are left at the end. So I've now got 0.0115 moles of ethanoic acid, and I've got 0.0105 moles of the anion. Now, in order to use these in my Ka expression, I don't want moles, I want concentration. So to work out the concentration, it's really important that I'm using the total volume. So that's going to include the 15 centimetres cubed of ethanoic acid and the 25 centimetres cubed of sodium ethanoate and the 1 centimetre cubed of sodium hydroxide. And it still needs to be in decimeters cubed. So here I'm going to be doing 0.0115 divided by 0.041. And that's going to give me a concentration of 0.280. And then if I do the same thing for my anions, I get a concentration of 0.256. So I can now put these together with my Ka expression. So I haven't written it out using the actual formula for ethanoic acid and so on here, although you absolutely could get questions where they ask you to do that specifically. But since this is just part of a calculation, it's fine for me to just say hydrogen ions and anions and the acid at the bottom. So if I rearrange that to make hydrogen ions my subject, and then I can work out what that concentration of hydrogen ions will be and substitute that into my standard pH calculation, and I get an answer of 4.73, which of course is given to 2 decimal places. Here's another example of the same type of question. Pause the video, work through the question on your own, and then when you're feeling confident that you've got the right answer, press play again so that we can go through it together. We start off in the same way by writing down the initial concentration of each one of the solutions. So 1.2 mole per decimetre cubed for my methanoic acid and 0.5 mole per decimetre cubed for my salt. And then I can do concentration multiplied by volume to give me the total number of moles for each of those substances. And then I need to think about how this is going to change when the potassium hydroxide is added. So potassium hydroxide, again, is a monobasic alkali, so for every 1 mole of potassium hydroxide there are 1 mole of hydroxide ions. So it's really straightforward, and it's also exactly the same as the previous question. So if I multiply the concentration of potassium hydroxide by the volume that I'm adding, I get 0.00048 moles. And since I'm adding alkali, that means that the concentration of my acid is going to decrease and the concentration of my anion is going to increase. So therefore, at the end of my reaction, I'm going to have 0.02352 moles of the acid left over and 0.01048 moles of the anion. So the acid has decreased because we're adding base, and the anion has increased. And then I'm going to join together the volumes of the methanoic acid and the potassium methanoate and the potassium hydroxide that's been added to that to give me a total volume of 41.2 centimetres cubed, so 0.0412 decimeters cubed. And when I do that division, I get a concentration of 0.57 for my acid and a concentration of 0.254 for my anion. So these are now going to be substituted back into my Ka expression. So again, we rearrange that, and then we put that hydrogen ion concentration into the pH calculation, and we get a pH of 3.40. Now let's look at adding a strong acid to an acidic buffer. Again, you need to recognise that these are equilibrium questions. It's just that everything is going to shift in the opposite direction. When you add an acid, you're therefore adding hydrogen ions, so the system will shift to remove those hydrogen ions and reduce the concentration of them. And the only way that it can do that is by those hydrogen ions associating with anions to form more of the acid. So this time around, the acid concentration is going to increase and the anion concentration is going to decrease. But apart from that, your whole method is going to be exactly the same as in the previous examples. You're still going to end up with the hydrogen ion concentration by using the acid dissociation constant Ka, and then once you have that, you can calculate pH. This question is very similar to the previous two we attempted, but in this instance, rather than adding a strong base, we're adding a strong acid. And just to make things slightly more complicated, I've picked a diprotic acid to add an extra bit of challenge in there. So we're going to start out in exactly the same way by writing down the concentrations of the two solutions that make up the buffer, and then multiplying those by the relevant volumes to work out how many moles of each there are. Now, in order to work out how those numbers of moles are going to change, we need to know how many moles of hydrogen ions are being added, not how many moles of acid are being added, although we are going to use the acid to work out the hydrogen ions. So I can work out the moles of sulfuric acid by multiplying the concentration by the volume to give me 0.0005 moles. But as we know, for every 1 mole of sulfuric acid, we're going to have 2 moles of hydrogen ions. So to work out the moles of hydrogen ions added, I actually need to double this number. Now, when those hydrogen ions are added, they are going to associate with the anions that have come from the salt in order to make more acid. So the number of my moles of acid is going to increase by this amount, and the number of moles of my anions is going to decrease by this amount because they've been taken up by those hydrogen ions. So then my moles at the end are going to be 0.041 and 0.003, and then I need to divide those by the total volume. So this is going to give me a concentration of 0.672, and likewise if I do the same for the anion, I get a concentration of 0.0492. So back to my expression for the acid dissociation constant Ka, and we rearrange this to work out the concentration of hydrogen ions, and then if I take the negative log base 10 of that hydrogen ion concentration, I get a pH of 2.61. Hopefully that made sense and you're ready to have a go at one of these on your own. So this question is in the same format as the previous question, except that this time I haven't given you a diprotic acid, so it's actually slightly simpler because you won't need to do that doubling step. So pause the video, work through the calculation on your own, and when you're feeling confident, press play again and we can go through the answer. Hopefully you started by writing down the concentration of each solution and multiplying those by the relevant volumes. You then need to work out how many moles of hydrogen ions you've added by looking at the concentration and the volume of the hydrochloric acid. The acid is going to increase by that number of moles, and the anion is going to decrease by that number of moles. And that gives us final moles of 0.017 and 0.008. And we then need to divide those by the total volume. And this is going to give us a concentration of 0.327 and 0.154. Again, we go back to our expression for Ka, we rearrange it to make hydrogen ions the subject, and then we put that answer into our pH calculation to get a final answer of 5.10. Thank you very much for watching, and I hope you're now feeling more confident in tackling this type of buffer question. If you did find it useful, then don't forget to like and subscribe for more A-level chemistry videos, and if there's a particular type of question that you would like me to cover, don't forget to let me know in the comments below.